Welcome to This Explainer. Today, we're going to dive into the hidden infrastructure that literally keeps our modern world functioning. Think about it. Massive manufacturing facilities, sprawling chemical plants, and municipal water management systems. They all have to run smoothly, efficiently, and above all, safely. But how do they actually pull that off? Well, today, we're demystifying the incredible instruments that make it all possible. Here is our roadmap. First, the high stakes. 2, pressure and buoyancy sensors. 3, wave-based measurement sensors. 4, electrical and extreme sensors. 5, translating signals to systems. And finally, 6, choosing the right transmitter. Let's jump right in. Section 1, the high stakes. Preventing disasters and saving millions. Picture this. You've got a massive storage tank full of highly corrosive, dangerous chemicals. You obviously can't just climb up, pop the lid, and peek inside with a flashlight to see if it's getting full, right? It's way too dangerous. The pressures are extreme, and honestly, human error just isn't an option here. So how do we prevent catastrophic overflows, keep expensive pumps from running dry and destroying themselves, and ultimately avoid massive environmental disasters? Well, the undisputed hero here is the level transmitter. It's essentially the eyes of the plant. By definition, it's an instrument that measures the exact level of a liquid, a thick slurry, or even dry solids inside a completely sealed vessel. But here's the kicker. It doesn't just measure it. It converts that physical reality into a standard electrical or digital signal, which means the plant's computers can continuously monitor and control the whole environment. And these things aren't just fancy measuring tapes. They are your absolute frontline defense for process safety, preventing overfills and equipment damage before they happen. They also vastly improve efficiency by optimizing inventory. Because you're getting continuous, real-time measurements that are highly accurate, they plug right into automatic alarm and control systems. That means pumps and valves are opening and closing all by themselves based on this data. Ultimately, this leads to massive cost savings by slashing downtime and reducing wasted materials. Now, the sheer variety of sensors we have out in the field is kind of staggering. We're talking about 10 distinct types of level transmitters used across the industry today. Everything from differential pressure and radar, all the way to capacitance and nuclear. To make sense of this whole landscape, we can actually group them into logical families based on exactly how they sense the physical world. Which brings us to Section 2, pressure and buoyancy sensors. Basically, measuring by feeling the weight and force. So this first family relies entirely on physical contact and force. You've got your differential pressure, or DP transmitters, which measure the pressure difference between the top and bottom of a closed tank. Super rugged, great for high heat. Then there are hydrostatic sensors. These are beautifully simple, often dropped right into water wells. They just calculate the weight or pressure of the liquid column sitting right above them. Next up are displacers. These rely on buoyancy. As the liquid rises, the displacer floats, which is awesome because it makes them immune to annoying variables like foam or temperature swings. Finally, magnetostrictive transmitters. These use a magnetic float riding along a waveguide. A pulse is sent down, and the physical twist in the waveguide gives us a ridiculously accurate continuous measurement. They literally feel exactly where the liquid is. Let's keep moving. Section 3, wave-based measurement sensors, bouncing signals to calculate distance. So now we're looking at non-contact methods, and it usually comes down to 2 heavy hitters, radar versus ultrasonic. Radar transmitters fire microwave signals down at the material and time the echo. The great thing about microwaves is that they don't care at all about air density, color, or pressure changes inside a closed tank, making them perfect for extreme chemical setups. On the flip side, ultrasonic transmitters use high-frequency sound waves. Now, while changes in the air can affect sound, these sensors are incredibly cost-effective, super easy to install, and absolutely ideal for open water and wastewater tanks where conditions are relatively stable. But what if your liquid is highly viscous, really corrosive, or just churning with heavy foam and vapors? A standard radar signal bouncing through the air might just get scattered. That's when you bring in a guided wave radar, or GWR. Instead of shooting microwaves through the open air, the radar pulse travels directly down a physical probe, like a metal rod or a flexible cable, cutting straight through the turbulence. When that pulse hits the material surface, the energy reflects back perfectly. It really is the best of both worlds. All right, Section 4, electrical and extreme sensors, harnessing conductivity and radiation. Sometimes we aren't just dealing with basic water or oil. For tricky materials, think tri-powders, grains, or conductive acids, we rely on pure electrical properties. Capacitance transmitters detect changes based on the material's dielectric constant as it covers a probe. The best part? Zero moving parts. That makes them fantastic for granular solids that would easily jam up a mechanical float. Conductivity transmitters, on the other hand, use the actual electrical conductivity of the liquid itself. When a conductive liquid, like an acid, touches the probe, it completes the circuit between electrodes, giving you an instant, rock-solid reading of the level. But here is a massive engineering challenge for you. How do you measure something that will essentially destroy any sensor it touches? Imagine a sealed reactor vessel full of boiling, corrosive slurry, completely pressurized. You can't drill a hole in it, and you certainly can't dip a probe inside. So what do? The answer sounds like straight-up science fiction, but it is an everyday reality in heavy industry. You use a nuclear or radiometric level transmitter. You take a heavily shielded radiation source and mount it on the outside of the tank. Then you place a detector on the exact opposite side. The radiation passes entirely through the solid steel walls of the vessel. Based on the attenuation principle, which is just a fancy way of saying how much radiation is blocked or absorbed by the material inside, that detector calculates exactly how full the tank is. You get to measure extreme, harsh process conditions without ever making physical contact. Pretty wild, right? Section 5. Translating signals to systems, connecting the sensor to the plant's brain.
So think of the transmitter as a universal translator. In step 1, it senses the physical change. Maybe that's a radar echo, a pressure drop, or a shift in capacitance. In step 2, the onboard electronics perform a crucial conversion, turning that physical reading into a standardized 4 to 20 milliamp DC electrical signal. Finally, in step 3, this signal is sent over the wires to the DCS or PLC. Those are the central computer brains of the plant, triggering alarms and automatic interlocks the second they're needed.
And there is a really elegant piece of math behind this communication that acts as a genius built-in safety feature. You might be wondering, if the tank is at 0%, why isn't the signal 0 milliamps? Why start at 4? Well, if the signal was 0 for an empty tank, the computer wouldn't know the difference between an empty tank and a wire that just physically snapped. By making empty equal to 4 milliamps, if a wire ever breaks and the signal drops to absolute 0, the system instantly knows there's a critical fault and sounds an alarm. From there, it scales up perfectly to 20 milliamps for a 100% full tank. Okay, our final stop, Section 6, choosing the right transmitter, navigating those crucial engineering decisions. Because you absolutely cannot just grab a transmitter off the shelf and hope for the best. Engineers have to meticulously weigh a ton of criteria. First, what exactly is the material? Is it a smooth liquid, a chunky slurry, or dry powder? What are the extremes for temperature and pressure? Is the tank open to the air, or is it a pressurized, closed vessel? They also have to account for headaches like corrosiveness, heavy foam, or vapor. Then, they balance the strict accuracy required against whether they want a contact or non-contact instrument, all while keeping the ever-present constraints of budget and long-term maintenance in mind. Ultimately, it's all about matching the unique physics of the sensor to the specific problem. Here's how that plays out in practice. If you've got foamy or vaporous materials that mess with sound waves, you go with guided wave radar or standard radar. If you need to measure the exact interface, the point where oil and water separate in the same tank, you'd use a displacer or guided wave radar. And for dry powders that would just jam up a mechanical float, you pivot to capacitance or radar. The level of thought and engineering packed into these relatively small devices is truly staggering. They are total unsung heroes of our industrial age. So the next time you drive past a massive industrial facility or a water treatment plant, don't just look at the giant steel structures. Ask yourself what unseen sensors, whether it's radar, ultrasonic, or even nuclear, are silently and accurately measuring the depths to keep everything perfectly balanced and utterly safe. Thanks so much for joining me on this explainer, and keep questioning how the world around you works.